And it's not okay. So my PowerPoints aren't in the actual Unit 2 folder. All right. So the main unit we're going to be going over is the 3 laws of motion. 6th grade, 6th or 7th. Yeah. We will be going in way more detail. Particularly Newton's second law. But today we'll focus on Newton's first law of motion. It's called the law of inertia. So Aristotle's classification of motion, natural motion, every object in the universe has a proper place determined by a combination of 4 elements: earth, water, air, and fire. Obviously this is wrong. Yes. Any object not in its proper place will strive to get there. For example, a stone want to get closer to the ground. Puffs of smoke rise up because smoke needs to be up in air. Stones need to be on the ground. So he described this natural motion. Straight up or straight down for all things on Earth. Beyond Earth, motion was circular. So he believed, Aristotle believed, and Earth was the center of the universe. The sun went around it. All the other planets went around it. And they realized this didn't work. They fixed this by making them also go into circles themselves. So to illustrate that, so he believed, I believe he believed it, or at least people before him believed it. So he had Earth in the middle, and he had, for example, the sun going around the Earth. And he had like planets also going around. However, some of the planets didn't match up. Sometimes they start moving backwards. So to solve this issue of going backwards, they made these objects. So again, Earth in the middle. The sun definitely went around. But to solve the fact that some objects appear to go backwards, what they did is they had like a planet go around in a circle, and this circle goes around like that. So occasionally the planet will be moving backwards, and occasionally it'll be moving forwards, and that's how he solved it. They assumed back in the past that basically everything moved in circles if it's not on Earth. Obviously, this isn't true. What solves the issue is putting Earth in the center. I'm putting the sun in the center of the universe, which is still wrong. We've now learned that there's galaxies and the rest. But beyond that, everything was circular. So the sun and moon continually circled the Earth. Violent motion produced by internal pushes and pulls on objects. So wind imposes motion on ships. And then we get to Galileo's concept of inertia. Galileo demonstrated Aristotle's assertions in the 1500s. Objects of different weight fall to ground at the same time in the absence of air resistance. So if you drop a feather and a hammer at the exact same time, they fall at the same rate. Did you know that? So, this is a correct video, but I want you to.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems at the same time to see which fell fastest.
So he has a bowling ball and a feather. Is it choppy for you? Okay.
Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air.
So, world's largest vacuum chamber. After removing the air.
5, 4. Cameras on. 2.
I do have something in the printer.
Release.
So they remove air. And it's a very light feather. And a bowling ball. And they hit at the exact same time.
Exactly. Look at that.
So objects on Earth fall at the same acceleration. There is a minor exception. So technically, whenever a feather or a piece of paper, if you take a piece of paper and drop it, the entire Earth moves up and the feather moves down. Because the feather exerts a gravity field around it and will pull the entire Earth upward at the same time the Earth pulls the feather downward. Now, obviously, the Earth is super, super big, so the amount the Earth moves up is a fraction of 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 the width of a proton. It probably doesn't move up at all. It's immeasurable. It is so small that you can't measure it. It's probably on the quantum level of movement, if that. It is so mind-bogglingly small that you wouldn't be able to see it. I'd write this number down. G equals 9.8 meters per second squared. I might use 9.81, but 9.8 is a good enough estimate. That is the acceleration of gravity on Earth. We'll calculate it after a while, or one day. But a moving object needs no force to keep it from moving in the absence of friction. So, a force is a push or a pull, and inertia is a property of matter to resist changes in motion. It depends on the amount of matter in an object. You can pass this one out. So inertia just depends on mass. The more inertia you have, the more resistance to change in motion. So inertia is going to be the resistance to change in motion. So if you have inertia, you're going to want to resist moving, or you want to resist slowing down. Galileo came up with the concept of inertia. Ball rolling on a downward slope picks up speed. As you rolling the ball up, a plane loses speed, so a ball on a horizontal plane maintains its speed indefinitely. You notice that it basically it maintains its speed on a horizontal plane. And if the ball comes to rest, it is due to its nature. It is not due to its nature, but due to friction. So the only reason the ball slows down was because there was friction. So the use of inclined planes in this experiment demonstrated the property of inertia. So the more steeper the hill, the more it slowed down. Or if it was downward sloped, it changed its speed. But if you didn't have a slope, it did not change its speed. So inertia is a property of matter and not a reason for the behavior of matter. So it's an inherent property of matter. If you have mass, you're going to have inertia. So Newton's first law of motion. Every object continues in a state of rest or uniform speed in a straight line unless acted on by a non-zero force. Net force. So, net force is key. For example, if I apply two forces here, these forces cancel each other out, so my hand stays still. If my right hand pushed more strongly, then I'll be pushing and moving to the left. So if the forces are equal, the reason why you aren't moving toward the center of the earth is because ground is pushing up on you with the exact same force as you were pushing down on the ground. They cancel each other out, so the net force is 0. Force is going to be a vector. So again, it's the difference between displacement and distance, or between velocity and speed. Velocity is a vector. Vectors simply have a quantity known as a magnitude. This is the number, how much, and a direction, which way. So vectors always have a magnitude and direction. They have a numerical value and a direction in which way they're going. So force always has a direction. So this can be represented by arrows drawn on the scale called vectors. The length of the arrow represents magnitude and arrowhead shows direction. We won't be doing graphical analysis of vectors. There's a way to actually, if you have grid paper, you can let like 1 inch be equal to 1 pound of force. And so what you could do is graphically draw. But you can see that could be a problem if you have 1,000 pounds of force versus 1 pound of force. It's really hard to draw that scale. So we don't do that here. But force, velocity, and acceleration all have directions and are all vectors. So net force is the combination of all forces that act on an object. So, and in this class, we will be using Newton as a force value. A Newton is equal to a kilogram times a meter per second squared. I might actually need you to print something out. Again, let me actually go ahead and do this. I'm going to go ahead and just print all the homeworks out. I really hate if I don't click on system properties first, it'll print it without staples and only print one copy. Actually, probably won't give the homework because I won't get to it. So, if you see a kilogram meter per second squared, you can replace those units with just the letter N for Newton. So if you have 5 newtons pull in the same direction, they'll combine together to equal 10 newtons. So the net force is just adding it together. If you're pulling on a box with 5 newtons of force in one direction, then pulling on it with 5 newtons of force in the other direction, they add together to cancel out. So what you do is you let one direction be positive, and so when you're doing the math, you'll let like to the right be positive and let to the left be negative. So you plug in -5 plus +5, and that equals 0. So a car is pulled to the right with a force of 15 newtons, while being pulled to the left with 20 newtons. The net force would be what? 5 newtons to the left. The two forces are in opposite directions, so they subtract, and the direction can be determined by the larger force. What I would do is always assume right is positive, so that'd be positive 15 plus negative 20, which gives you -5, and then you remove the negative and positive signs and indicate which direction they represented. So what is the net force on this box? 5 to the right. So vector quantities have magnitude and direction. They're represented by arrow. We're not really going to be doing that. Then we have scalar quantities. They only have a magnitude. So mass, volume, and speed are scalar. Mass has no direction. Time, we usually represent time as a scalar, unless you're in advanced general relativity, in which case time is its own dimension. You have space-time. So there's not only is there up, down, left, right, forward, backward, there's also a forward in time or backward in time, according to the math. But we'll treat time as a scalar too. 5 seconds isn't 5 seconds in the future. Technically, you could solve for -5 seconds, which the negative would mean backwards in the future. It happened in the past. But when writing it out, we'll treat it as a scalar. So adding up 2 or more vectors will require the Pythagorean theorem. Right now, we're not doing 2D yet, so I'm going to skip this right now. Note that, yeah, I'll skip this. I'll go over this in another time. Right now, vectors is not important. So the vector sum of forces acting on a non-accelerating object is equal to 0. That's a good thing to note. If you are not accelerating, the sum of forces is equal to 0. It looks like an E. So this symbol right here, I do use math notation in physics. So this E is the Greek letter F. So it's the Greek capital letter epsilon. It's the equivalent to a capital S. It looks like this, and it stands for sum of. So saying epsilon F, I don't even say epsilon, I say sum of. So sum of forces equals 0. So if something isn't accelerating, if its speed is staying constant, that means that the sum of all forces on the object is equal to 0. So here you see that So he's standing on a beam. You have two ropes pulling up, so that's a force. You have the weight of the board pulling down because of gravity, and then you have the two weights of the two people pulling down. That means that all those 1, 2, 3, 4, 5 forces have to sum to equal to 0 if that board isn't changing its speed or rotating. So if it isn't moving, or if its speed isn't changing, it means that every single force in the entire problem has a sum equal to 0. This is known as the equilibrium rule. So this applies to vector quantities. So direction is what enables it. We have a support force called a normal force. Is an upward force on an object that is opposite to the force of gravity. So a book on a table compresses atoms in the table. So if you put an object on your desk, it's going to compress and push down on the atoms. And because they're being compressed, they're kind of like a spring, they're going to push back up. And because the book isn't moving, that means that the sum of forces, the atoms pushing upward and the book pushing downward, have to cancel each other out. So if you push down on a spring, the spring pushes back up on you. Similarly, when a book pushes down on a table, the table pushes back up. Because it's not changing its speed, that means that all of the forces of every atom is perfectly counteracting all the forces of the atoms in the book. When you stand on two scales, 1 foot on each scale, and you weigh yourself, your weight is evenly distributed. Each scale would read half your weight. Because you have your 1 foot is pushing down on one, 1 foot is pushing down on the other. That means they'll both push back upward, and the scale reads how much force pushing back upward. So you have a force of your weight downward, and the two scales will be pushing upward, and both of them read each force they're pushing upward, and so they'll have 1/2 your weight. Equilibrium is a state of no change when no force is acting on it. So we have static equilibrium, so a hockey puck at rest on slippery ice. We also could have dynamic equilibrium, where the hockey puck is sliding at a constant speed. This is still equilibrium because its speed isn't changing. So an equilibrium test, whether something undergoes change in motion. A crate at rest is in static equilibrium. There's no change in motion. When pushed at steady speed, it's in dynamic equilibrium. You don't really need to know the difference between here. I won't test over it. A bowling ball is in equilibrium when it's in rest and when it moves in a straight line. I don't really think I test over equilibrium. So again, I don't test over this. Let's see. So you're riding in a vehicle with a steady speed and toss a coin straight upward. It will return back into your hand because it was initially moving forward. And when you throw it upward, it'll fall straight back into your hand because both you and the coin are moving forward. And the only change you're doing is an upward force, and so gravity will pull it back down. What you won't see is it'll go and be left in the same spot as you and the car continue moving. So due to the coin's inertia, it continues sideways with the same speed as the vehicle, and then it moves up and down. I think I won't give homework today. I'll give it tomorrow. I'll go over this PowerPoint and see how far I get. And because this is the more important one, I'll probably continue it in more detail tomorrow. which gives us Newton's second law. So Newton's second law. Forces cause acceleration. Acceleration is directly proportional to net force. To increase acceleration on an object, you must increase the net force on it. This symbol right here is a tilde on the keyboard. It means proportional to. So I'd write that down. This tilde, at least I call it a tilde, is technically in math, it's called proportional to. And I will go ahead and do this too. If you have two of them on top of each other, do you know what this means? If you have two of them, similar, it's approximately equal to. So one of them just means it's proportional to it. As one goes up, the other goes up. Whereas this symbol means it's approximately equal to. They're about the same. We have a lot of math notation in physics. So, force of friction depends on the kind of materials and how much they are pressed together. Is due to tiny surface bumps and to stickiness of the atoms on the material surface. So friction between a crate on a smooth wooden floor is less than on a rough floor. Even if two objects look very smooth, on the atomic level they have tiny little bumps in them. Also, the bonds of one object, the atoms of one object, will try to slightly bond with the atoms of another object. These bonds are so weak that if you push on it, it'll break and cause sliding. But the force of friction can occur when sliding, if you're in water or air. In water, it's water resistance, and air is air resistance. And when it's just sliding object, we just call that friction. Friction can air resistance is a form of friction. It's air friction. The friction can occur for objects at rest. If you push horizontally on your book and it doesn't move, it's because the friction between the book and the table is equal and opposite to your push. In fact, in order to get something to move, you have to break something called static friction. Static friction is the friction that will keep it from moving. And if you might have realized this, if you start pushing on something very heavy, as soon as you get it moving, it's more easier to keep moving, right? And what happens is there's two frictions. There's a sliding friction, it's the friction after it's moving, and then there's a static friction that you have to overcome to get it moving. And for some objects, static friction can be quite high or lower than sliding friction. So if you have like a cardboard box that's very rough on a carpet floor, it might have very high static friction. Or if you had rubber on like a smooth floor, the rubber can really eat into the smoothness of the floor and be very hard to get. But as soon as you break static friction, you're now only dealing with sliding friction, and sliding friction can be different. So when Sanji pushes a refrigerator across the kitchen floor at constant speed, the force of friction between the refrigerator and the floor must be what? So it's at constant speed. Constant speed means the net force is equal to 0. So it's equal because if it's not accelerating, meaning that it's staying at rest or staying at constant speed, that means that the sum of forces has to be 0. That's a very important fact you have to always think of. That's the first thing I would think of. Is it accelerating? If it's not accelerating, all the forces have to be equal. So since it's at constant speed, that means the friction force has to equal the force that you're pushing it. If it's at increasing speed, that means that the friction isn't slowing it down. Your push is greater. So the amount of friction has to be less than your push. And it's not in equilibrium. Mass is the quantity of matter in an object. So how much matter is in an object is also the measure of the inertia or sluggishness that an object exhibits in response to any effort made to start it, stop it, or change its position. You can think of mass as inertia or inertia as mass. Weight is going to be your force due to gravity. Note in or English or in America, we tend to treat. Actually, they do it too in metric. We tend to use force, pounds, for weight, and not mass. We've recently, I forget when they did it, we have something called a pound force, and we have a pound mass, and we set them equal to each other on Earth. But we use metric system. Kilogram will be mass, and weight will be newtons. So mass is the measure of the inertia of material. Is independent of gravity, so you'll have the same mass on Earth as you do in outer space or on the moon, and we'll be using kilogram to do it. Weight is going to be the force on an object due to gravity. We will be using the Newton. In America, we usually use pounds, but we won't be doing it in this class. So if the mass of an object is halved, the weight of the object will also be halved, because weight and mass are directly proportional to each other. Oh, it's 35. I thought it was 25. I was like, shouldn't the bell already ring? I was rushing. So mass and weight are usually interchangeable in everyday language. Mass, however, is very different and more fundamental than weight. We tend to only use mass in science. So on the moon, the weight of an object on the moon is less than on Earth, but mass will be the same in both locations. Since you're probably not used to kilograms, you can just remember that 1 kilogram is equal to 2.2 pounds, which is equal to about 9.8 newtons. Note here that in this PowerPoint, they use 10 newtons, they round. Don't round. It's 9.8 newtons. So you can do 1 kilogram is equal to 2.2 pounds or 9.8 newtons. And thus a pound is about 4.45 newtons. Yeah, 4.5 carried. So you need to convert between newtons and pounds to see. But I tend to make up very strange numbers. I just make up numbers. So a lot of times I might give you a 1,000-pound guy. I usually try to keep it consistent. Like I'll use 100 kilograms or 50 kilograms. 100 kilograms will be 220-pound guy. 100 would be 50 would be 120. When the string is pulled down slowly, the top string breaks, which results in so when the string is pulled down slowly, the top string breaks, which best illustrates the weight of the ball. Tension on the top of the string is pulling tension plus the weight of the ball, both of which break the top string. If you pull down quickly, this would be more a result of the mass of the ball. It is the laziness of the ball that tends to keep it at rest, resulting in the breaking of the bottom string. So if you pull down very slowly, the top string is holding it more of the weight of the ball. However, if you pull super quickly, the bottom string will break. And that is because the ball, if you pull super quickly, the ball, because of its mass and inertia, is going to stay still. So if you pull super quickly, the ball is going to stay still because of its inertia, and so you're just going to break the bottom string. However, if you pull slowly, more likely what would happen is the top string would break, because the taut string would be a combination of both the weight of the ball and the force in your hand. So, the same force applied to twice the mass produces half the acceleration. Mass, or inertia, resists acceleration. 3 times the mass produces 1/3 the acceleration. So, here, if you have it like acceleration is proportional to 1 over mass. If it's 1 over mass, another way of saying this is that acceleration is inversely proportional to mass. As mass goes up, the acceleration goes down. So Isaac Newton was the first to connect the concepts of force and mass to produce acceleration, which gives us Newton's second law. Newton's second law, the law of acceleration, relates acceleration and force. And this is on that handout I gave you. The acceleration produced by a net force on an object is directly proportional to the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. Written in equation form, acceleration equals net force divided by mass. I do not recommend remembering this equation like this. I remember F equals ma. Technically, it's the sum of F, sum of forces is equal to mass times ma. So, net force is going to be represented by epsilon F. The sum of forces is your net force. So, F equals ma is going to be your main equation. If net force acting on an object is doubled, its acceleration is doubled. So, force is directly proportional to acceleration, and is directly proportional to mass. If the mass of the object is doubled, object's acceleration would be halved. So if mass goes up and the force stays the same, acceleration must go down. So force of hand accelerates the brick. If you apply twice the force, you get twice as much acceleration. However, if you do twice the force and twice the mass will counteract twice the force, giving you the same acceleration as just pushing with one hand on a brick. If you do the same force on 2 bricks, you'll get half as much because you doubled the mass. Acceleration would half. I think I said that wrong. If you do the same force on 2 bricks, you get half as much acceleration. And if you do the same force on 3 bricks, you get 1/3. So consider a cart pushed along a track with a certain force. If the force remains the same while the mass on the cart decreases to half, the acceleration of the cart would double. I guess I'm going to stop here today. I'll finish it tomorrow. These PowerPoints, they're nice to have, but I'm just going to go over all the math when I finish them. It's just something you can go back and look at definitions on.